Hello students, Assalamu alaikum. I hope you will be fine and okay. In today's lecture we have to start little bit about in detail again about the above principle and electronic configuration of the transition elements. There is two places where above principle cannot be followed. I have a little bit shown you earlier that how above principle can help you by in electronic configuration. For example, there are four orbital s, p, d and f. According to quantum mechanics, they have started on their own principal quantum number. For example, s start from 1s, p start from 2 and d start from 3 and 4 and f start from 4th period respectively. So that is why they are according to their place, and we have to fill electron according to their energy level. For example, electron will go first in 1s orbital, then goes to 2s orbital, then goes to 2p, then 3s, then 3p and 4s, and then comes 3d, 4p, 5s and so on, which you have seen here also. How can a number of electron can be filled? Here you can remember also one point that S have maximum electron 2. The p subshell can accommodate maximum electron of 6. The d subshell accommodate maximum 10, and the f orbital can maximum hold up to 10 electron. So this is the little bit summary about the above principle. Similarly, you have to follow Hund's rule, Pauli exclusive principle accordingly. As according to Hund's rule, when there is empty space, you have to not to pair the electron, and electron have to go singly in each subshell. Now when comes toward the electronic configuration of transition element, there are comes two places where this rule is not followed. For example, in chromium, which has atomic number 24, and copper, which has atomic number 29. For example, if we are filling these 24 electron by above principle 1s2, 2s2, 2p6, 3s2, 3p6, according to above principle, this electronic configuration is equal to, in almost cases of the table, is equal to argon, which has 18 atomic number. So the 18 electron has been shown here. Now we have left 6 electron. How we have to place these 6 electron? In the upper example, you see that the 4s orbital subshell come first and the 3d subshell orbital comes later. So according to above principle, we have to first fill s orbital here, here and here also. But what's the problem here is that we have 6 electron and we put if the 2 electron here, so then there is left just 4 electron. 2, 1 makes 3, 4, 5 and 6, and this electron you have left vacant. Here is now it is filled, which I have explained you later, but this is not the case, because here if you see that all the orbital occupied single electron, and this is called half shell electronic configuration, which is more stable in this case. So the second electron of this 4s subshell goes here to fill the empty 5th d subshell 3d orbital. So that is why this make happen. I have to show you in the other example in how it would be happen. You can understand clearly. Let's see, student, we have to draw the electronic configuration of chromium and copper, which have 24 and 29 atomic number, means that it has 24 electron and copper has 29 electron. We draw here the 4 possible subshell. that according to Abba principle, that is 1s, 2s, 3s, 4s, 5s, 2s, 3s. So electron goes first in this subshell 1s2, then goes in this subshell 2s2, then goes in 2p 3s2, then the number comes 3s2, and then 3p and 4s2. At 3p 6, this is the electronic configuration of argon. Now we have to go forward, that is 4s2, and then we have to fill 3d4. For example, we have to accommodate just 24 electron. If you see, this electronic configuration is totally according to above principle. So this is the last shell. So what the problem is here, which I told you earlier, that here is 4s2 and 3d4, and if you remember, D have 5 subshells or 5 orientations. So if we accommodate the 2 electron here, then we have 1, 2, 3, 4, and this last orientation can be vacant. So for accommodating this last subshell, we have to transfer this electron from here to here, which make possible for us. So this electron, if not goes here, this left vacant, which is violation according to thermodynamics rules. As in this, if you remember, I show you in the last slides that the 4s orbital is quite near and resembles with 3d subshell. That is why the transfer of electron is much easy. So that is why we have not to follow that type of configuration according to our principle. So the green means 4s1, 1 minus here, and 3d5 is okay electronic configuration. Then if we move forward, the same situation we have got here, 3p6 up till it is argon, then we have 4s2, then 3d9 to accommodate 29 electron. Here the full subshell electronic configuration is more stable than a half. As we discuss here, it is a half filled electronic configuration, means 5 electron out of 10, and here is 10 by 10. So this electronic configuration is more stable, which I have to want to explain. So I hope you will be understand now. So that what I was explaining to you in the later example. You may see here in the description also that the valence electronic configuration of the first row transition series have 2 anomaly, and the 3D series comes in 4 period. That is why, if you remember, we just draw previously a formula that 4n is equal to that 4s 2 n minus 1 d, and d is filled from 1 electron up to 10, because d have maximum capacity of 10 electron. So here if you see that according to our principle, the chromium follows the electronic configuration of 4s2 3d4, which is not correct. We have to follow the 4s1 3d5 electronic configuration. And similarly for copper, that is 4s1 3d10. So what the things common here, if you see 3d5 and 3d10, so 3d10 is a full filled electronic configuration, more stable as compared to 3d9, and similarly 3d5 is a half filled electronic configuration, which is more stable as compared to 3d4. So that is why the original electronic configuration is this, not this, and similarly the original electronic configuration of copper is this, not this one. There is maybe some people ask a question that how can it do so. As I explained in the previous slides, and now here is one demonstration also, that S is a smaller orbital which have circular in shape, but as with the increase of the principal quantum number, the size of the s orbital goes bigger. For example, if we start from 1s, then 2s is bigger than 1s, then 3s is also bigger than 2s, and similarly that 4s is, if you see, it is quite equal in size with the 3d orbital. So these are all 3d orbital overlap with each other, but here surrounding the 4s orbital also. So electron is very easily transferred from this 4s orbital to this 3d orbital, but not in every case, just in the case of, for example, in chromium or copper, where we have 3d 4 configuration without the addition of electron, and where we have 3d 9 electronic configuration in copper without adding the 4s orbital there. So we have to add electron here. If you see some of the slide here, I will be also maybe explain to you. Here is 1s orbital, lower in energy, then after 1s there is a 2s orbital, higher in energy, then 3s, then 4. Look here that this 4s orbital is comparatively equal in energy with 3d orbital, or equal, not I am saying that equal in shape, but equal in energy, but the shape of d orbital is just like this, and the shape of s orbital, but at this level the 4s orbital is quite bigger to surround the 3d orbital. So that is why when needed, or when need stability, it is very easy the s orbital to give an electron to the 3d orbital of the chromium or 3d orbital of the copper. Here is, you may observe some of the other parameters of the magnetic property also. Here you see that there are most of the electron are singly, so they are quite very easy to rotate and spin, so that spin can enhance its magnetic property. From this electronic configuration of transition element, we understand by another, we reach to another conclusion also, that here in the definition, that transition element are those elements which have partially d or f subshell, or this means that the d and f orbital are in the process of completion, whether in their oxidation state or whether in their ground state. So here if we see in this configuration, just like you see here, we have two examples, one is copper and another is zinc. What we are seeing here, that the d orbital is completely filled, so this d orbital completion does not fit according to the definition of transition element. They are placed rather in the group of the transition element or in the d block in the periodic table, but according to definition, their electronic configuration cannot fulfill or according to the definition, because if you see here, the d orbital is completely filled and here is completely filled. Whether it is in oxidation state, if they lost electron, or they have the d orbital in the process of completion, then they may have term, or they may have show the property of transition element. This there are some violation in the electronic configuration of the f orbital f block element also. For example, if you see here, there are in the last cases of terbium and lutetium, the f orbital is complete. And there are also more violation here, as because there are more electron, more orbitals, so there may have more electronic configuration. That the expected electronic configuration means the configuration according to above principle, but observed electronic configuration means the electron are shifted from the nearby orbital to the other orbital. And here is one that we have to see the d orbital also, the d orbital in the process of completion also, so it can hold the or hold the definition of transition element. So that is why that in the upper situation, when the shape of s orbital goes bigger and bigger, so it's very quite easy to submerge between the neighboring d orbital, whether 3d, whether 4d, whether 4f, or whether 5f. So as you go upward, the s orbital shapes quite increase in size, and this turns into submerge with the neighboring orbital. So that is why electrons are shifting. And similarly, as you see, there is how much single electron, this also behave the magnetic property. So as the element have more unpaired electron or single electron which all have similar spin, so they show more magnetic property. For example, here is one single electron, so it show magnetic property, but this scandium show less magnetic property than this another member, and then from another member. And if you see in this table, chromium has the maximum number of unpaired electron, so this unpaired electron behave the property of showing much magnetic property as compared to the all of the rest of the element. So the same is the case here. And if you see here in the copper and zinc, in the ground state, in the d orbital, there is no unpaired electron, just copper show a little bit magnetism due to a single electron present in the 4s subshell. But in case of zinc, in the ground state, it has no single electron, so zinc is diamagnetic, it has no it shows no magnetic properties. So next we have to discuss a little bit about the properties of the transition element. As you know, there are the transition element mostly are elements. So what the elements are behave as a metal. So normally what the property of the metal have, so most of the transition metal follows the property of metal, as the metals are usually hard, solid, and they have high melting and boiling point. So similarly, transition element have also high melting and boiling point. They often they are all paramagnetic, which we have discussed in electronic configuration. You see that in each element which has unpaired electron, so it is more paramagnetic, and similarly they have more oxidation state, and this oxidation state is also due to the presence of 4s and 3d orbital, that these 4s and 3d orbital are in outermost, and they are quite far from the nucleus. So that is why very easy to lose an electron. So depending upon the situation, transition element may lose 1 electron, 2 electron, 3 electron, 4 electron. So they have several transition states. Similarly, they have a color compound. As I explained, we have to explain this in CFT, crystal field theory, but if you show that there is shifting of electron from higher energy to lower energy. When electron jump from higher energy to lower energy, it emit radiation of a certain wavelength, and this certain wavelength can cause of a color. This wavelength have a color, and usually if it fall in the visible region, so it give us a color, which we have to explain in lateral theory. Secondly, the transitional elements have much famous property of to form complexes or coordination compound. That is why they have show good catalyst. They have catalytic properties, and that catalyst has to be used in the industry and in various fields. So which we see transition element have make complex sign or coordination compound. That is why you see in the electronic configuration that d orbital have still empty orientation. So you some of the ligand may transfer the electron and make a coordinate covalent bond. So they have a good property to make a complex sign. They are a good conductor of heat and electricity, as you see that there are some of the surface electron, and that is why a copper has a good conductor of electricity. And similarly, there is another property which metal possess. Transition metal also possess, that they can be drawn into sheets and wire, or simply they are malleable and ductile. So they can be hammered, they can be bent, they can be transferred into many shapes, wire and rods, as you see some of the industrial products of the metal. So transition metal is also part of them. So there are this property we have to discuss a little bit in the metallic bond. If you see in the metallic bond, there are electron surrounding each of the central nucleus. For example, this is the metal of one the nucleus of one atom, this is the nucleus of another, and so on. This is one demonstration, this is another demonstration, and the smaller particle which you see here are the electron. If I show you this slide in the animated form, so you may see here that electron from the nucleus is running from one area to another area. So this, if you closely observe, that these electrons can act as a glue and to hold an atom very strongly, and due to this the metal is quite hard and it can be transferred into many shape. It can be bended without losing, without loss its physical behavior. So that is why this property cannot be found in the another material you see around us, for example, just like stones and wood. But in metals there are free electrons. These free electrons are free to move from one place to another, and that is quite easy to be metal can be strong, and these properties is also explaining how metal are good conductor of electricity. So they are free electron and electricity can be passed very easily.